My name is Karthik Ramasubramanian. I'm from Texas Instruments. We also have my colleague Akshay, who's the primary point of contact for the workshop project. So the title of my talk is Evolution of Radar-Based Sensing and Opportunities for AI/ML. Is there a pointer? Oh, that's okay. Thank you. Thanks. Okay. So here's the outline of my talk. So we'll start with an introduction to radar. We'll talk about the applications of radar. The applications of radar have been evolving over the last several decades, getting into more and more civilian and commercial personal electronics type applications. Then we'll get into a little bit of a tutorial mode where we'll talk about FMCW radar, which is frequency modulated continuous wave radar, and how it operates and how the whole concept works. We'll discuss the advantages, why radar compared to maybe other sensing modalities. Then we'll talk about what are the key challenges in this space and what are the opportunities for AI/ML techniques in radar, and then we'll conclude. So here's just a quick introduction. I think we all know what radar is. Radar is radio detection and ranging. It's a technology that uses radio waves to detect, locate, and track objects. So the transmitter emits radio waves which then get reflected from the various targets, and the receiver analyzes the received signal, and you can determine both the distance, the velocity, and the direction of all the objects. And this technology has been in existence for several decades. It started off maybe 100 years back in the military and defense area. There has been use of radar in weather forecasting and Doppler radars for law enforcement and so on. But in the last several years, the use of radar has grown exponentially. Specifically in automotive world, where there are a lot of ADAS applications. ADAS stands for Automotive Driver Assistance Systems, where radars are used to detect other vehicles and automated driving and so on. There are also other applications in automotive which we call as body and chassis. I'll talk more about these applications in the next few slides. And then there are also industrial and personal and consumer electronics applications. For example, factory automation, home automation, smart homes, building automation. So these are all newer applications of radar that have been emerging in the last several years. And overall, radar has penetrated into a lot of these spaces, and there is a lot more that could be done with radar. So the focus of this talk is going to be millimeter wave radar sensing for some of these emerging applications. What are the key challenges and what are the opportunities here? Okay. And feel free to stop me anywhere if you have any questions.
Yeah, so is millimeter wave radar the latest version of radar, or what is it?
So I'll talk about what is millimeter wave radar, but basically millimeter wave radar, of course, is radars that operate, at the millimeter wave frequency bands.
Okay, prior
So
it was not operating on millimeter wave band.
So different bands have been used for radar. For example, there has been 24 gigahertz radars. There is sub 10 gigahertz also being used. But I'll talk about some of the advantages of millimeter wave radar because of the availability of higher bandwidth and higher RF frequency. There are some advantages, and these are bands that are dedicated for these applications. For example, the 77 gigahertz band is dedicated for automotive, and industrial applications are using the 60 gigahertz band where there is more regulatory license-free operation capability. Okay, so starting off with automotive applications, I mentioned that the use of radar in these kind of applications started a couple of decades back in the early 2000s, where Mercedes introduced a front radar for the first time in vehicles. So that was done for the purpose of adaptive cruise control, where you have the car in front of you and you measure the distance to the car and you're able to follow it at a certain distance. So that is adaptive cruise control feature. That was one of the first uses of radar in automotive. Then it got expanded to additional use cases where if there is a potential collision situation, then the car can do autonomous emergency braking. And these are operating in 76 to 77 gigahertz band. Then it evolved into more applications all around the car. For example, 2 corner radars were introduced for blind spot detection and lane change assistance. And also for front cross traffic alert, 2 front corner radars were introduced. And these corner radars usually started off in 24 gigahertz band. But then over the last few years, they've all moved towards 77 gigahertz band because of better performance. And more recently, we also see the trend that there are newer use cases emerging. So there is rear collision warning, and also radars all around, including some side radars, which can look on the sides to see if there is a target or object. Also parking assist is another application that's possible with radar. And so you see that there could be 8 to 9 sensors per vehicle to do all of the ADAS functionality.
The rear collision, it is implemented in any of the vehicle as well?
Yes, rear sensors are also there today. It looks behind and tries to see if it can avoid some rear collision situations. Yeah.
So why is there a difference between the resolution of front corner and back corner radars?
So typically, the longer range radars are configured to have kind of less resolution because you're looking farther and you don't need to have a very high resolution at that distance. So it helps to save memory and compute. If you try to do long range radar with, let's say, centimeter level resolution, you need to have that much more memory and compute. So typically it's just a configuration about how much bandwidth you use, what is the signaling waveform, and the resolution is directly proportional to how much bandwidth you're using. So usually long range radars are configured to use lesser bandwidth because you don't need very high resolution for those distances. And corner radars or even short range radars, typically, like for example the ones that you might use for parking assist, let's say your total distance that you need to measure is only 10 meters. But you want to know whether you are like within 3 centimeters or 5 centimeters at that distance. So there you configure it for very high resolution, but you don't need very high range. So it's just that typically the configurations, in order to optimize memory and compute, they are done such that long range is done with less resolution, short range is done with higher resolution.
For lane change assist with the camera and AI solution, it's if we can know how efficient, comparative to the radar,
Yeah.
which one will be better?
Yeah, so I have a slide coming down later about camera versus radar, what are the advantages and disadvantages. But basically, there are advantages in weather conditions. So you have radars can work in fog, dust, smoke. Cameras can fail in those conditions. Similarly, you have it can operate behind some plastic enclosures, which is advantageous in industrial type applications. So those are some of the key advantages of radar.
Cost, how radar will be which one will be better to choose in terms of cost?
So that really depends on what problem you're trying to solve. So radars, there is a variety of radar offerings, let's say, all the way from one transmitter, one receiver to, you can put a radar sensor together with like 32 transmitters, 32 receivers. So depending on that, the cost could vary. And I imagine the similar thing applies for camera systems as well, where depending on what you're trying to do, the cost can vary. So it boils down to what is the end application at the end of the day. But in general, I would say that for basically measuring distance, and let's say you're just looking for some proximity or something like that, you can do that with radar at a much lower cost than a camera-based system. Yeah, so for many industrial applications, for example, there can be a cost saving with radar. At least it can be a sensor that triggers the camera. Once you detect something, then maybe you want to trigger a camera. Maybe the camera system will consume more power, and for certain battery operated applications, you can use radar as a technology which does the first triggering, and then the camera can do recording in case there is someone from.
Kind of sensor fusion.
Yes, yeah. For security application, for example, at low power, you use radar to detect, and then you trigger a camera if there is something of interest that you want to then record or analyze, something like that. Yeah. Okay, so the other set of automotive applications is related to what we call body and chassis. So here, for example, you can have a radar in the interior of a car. This is typically a 60 gigahertz radar, which can be used to do child presence detection. So in Europe, for example, and also in other regions, there is emerging regulations which give you higher star rating for your vehicle if you're able to do this. So this technology can be used to avoid what is called as hot car deaths, where maybe a child is left behind inadvertently in the car in the hot sun, and the presence of a radar to monitor the vehicle when there is no one around, and then alert if there is a child left behind. So that is one application which is kind of over the last 4 or 5 years, it has kind of picked up with 60 gigahertz radar. We also have, once you have a radar in the vehicle, you can also do other things like intrusion detection, where you can monitor around your car to see if there is someone lurking around the vehicle. And then you can also then do seatbelt reminder type functionality. So today seatbelt reminders for passenger seats or passenger seats are based on weight sensors, but those can have false trigger problems, because if you have an inanimate object, then it can trip the weight sensor. Whereas radar, doing classification with radar, if you can detect humans versus non-humans using radar, then you can avoid that kind of a false alarm situation. So seatbelt reminders, another functionality that radar can do. Similarly, exterior of the vehicle, kick to open is one example of what we call hands-free access. Using a kick gesture, getting the trunk opened. Similarly, near field obstacle detection, where the radar can be used to detect if when you open the door it's going to hit something, for example. So these are all emerging applications in the automotive space. In terms of industrial applications, and a large part of this talk and the workshop project that we announced yesterday is in this space. So these are kind of also newer applications for radar. Radars can be used in industrial, robotics, and factory automation conditions, where you can look for obstacles or you can look for human beings around. Fluid level sensing and solid volume identification. This is an area where you're trying to measure the level of the liquid in a tank, for example. Traffic monitoring and traffic light control. But the consumer electronics is a very interesting area where radars can be used in doorbells. You're trying to look for someone who's approaching your door, or in air conditioners where you want to direct the airflow towards or away from the person's. Automated lighting, which can bring energy efficiency. You only turn on or turn off the lights depending on the presence of a person. Smoke alarms, thermostats. So all of these thermostats, for example, can bring great energy efficiency with radar and automatic temperature controls. So these are all applications in industrial which are of high interest, and I'll talk later about this. One of the key challenges with radar is can you do classification with radar where you want to trigger whether the detection is from a human or from a non-human motion, for example. So those are the problem statements that we'll talk further about, and this is going to be a key focus area for this talk. Besides that, there are also various other applications, vital sign monitoring, elderly monitoring, and fault detection, which could all have interesting applications and benefits. So why millimeter wave radar sensing? So millimeter wave, as I mentioned earlier, wavelength is of the order of a few millimeters. It's 30 to 300 gigahertz frequency band. And why radar now is because of various technological advances that have happened in the last 2 decades, which have led to smaller size, lower cost, and higher performance radars. So for example, if you see, these are 2 devices from TI. At 60 gigahertz and at 77 gigahertz. So this device, for example, includes the entire RF and compute functionality in a single chip. So you have, in this case, 2 transmitters, 3 receivers operating at 60 gigahertz band, and all the ADC data is processed on chip, and you can do detection and send the final result outside the device. So basically it allows, and also the antennas are on the package. So basically it all allows smaller size, lower cost and higher performance. So that is one reason why radars are becoming very interesting for all these applications. The second thing, of course, is that you can do all of these, you can solve all of these problems that I talked about earlier, and so there is a wide variety of applications that are emerging, and so that makes it very interesting. Now, what are the benefits of millimeter wave radar? At higher frequencies, you have access to wider RF bandwidths. For example, in 77 gigahertz, you have access to 4 to 5 gigahertz of RF bandwidth, and at 60 gigahertz, you have 7 gigahertz of RF bandwidth available, and this enables very good centimeter level ranging resolution, so that's beneficial. Also, the short wavelengths and high RF frequencies, it allows compact antenna arrays. So for example, in this chip, for 2 transmit, 3 receive, you would have 6 antennas on the package itself. For example, with the AOP or antenna on package approach. So that allows a very small form factor that you can put in various small spaces. And also you get excellent velocity resolution because of the higher RF frequency. The Doppler that you can measure will have very good resolution. So that's the other advantage of the millimeter wave. And you can do 4D measurements, so you measure range and velocity, but also you can do 2-dimensional angle measurements, so you can get azimuth as well as elevation depending on how the antenna is configured. So with all of this, and you pair this with AI or ML algorithms, we can push the bounds for applications across all this automotive, smart home, robotics and industrial spaces.
How large are the chips?
Sorry?
How physically large are the chips?
So these would be, I think, so this one is about 6 by 5 or 6 by 7, something like that, mm.
Okay.
Yeah, yeah. So comparison to vision, so the benefits of radar, as I alluded to earlier when answering your question, operation in dazzling light or no ambient light, so radar doesn't need ambient light, it can operate in the dark, and that's an advantage if your application requires you to do occupancy detection, for example, when there is no lighting, right? So radars can work in that case. It's robust to environmental conditions, dust, fog, smoke, rain, these conditions it can do better compared to vision-based sensing. Operation behind plastic enclosure, this is also very important in various use cases where privacy is important. So for example, we talked about applications like thermostat or smoke alarms and those applications where you cannot necessarily use a camera-based approach because of privacy concerns, and there radars will be a convenient technique because you can put them behind plastic enclosures. There is no issue of privacy in that case. So if you see a comparison between radar and vision, radars can give very good range resolution and velocity resolution, so you get direct measurement of range and speed. You get all-weather capability and you have privacy advantages. On the other hand, what radar is lacking in is what we call spatial resolution. So if you see this picture, so let's say there is a radar and there is a target. You measure the range and velocity with very high accuracy. So this is divided into some number of bins as per the range resolution and some number of bins as per the velocity resolution. You'll find that radar will pinpoint the range and velocity of the target with a very high resolution and precision. But if you have many targets or many objects in the same range and velocity, then in the angle dimension, it's going to be a blur of some sort. If it's a single object, then you can get the angle fairly accurately. But if there are many objects, it's kind of like a blurred view. And that's got to do with the fact that at the end of the day, you're not going to have like a 64 by 64 image like a camera, right? You're going to have a few antennas and each antenna is going to sense something, and you might have, let's say, 10 virtual elements or 15 virtual elements. And that's going to give you information about the angle, but it's not going to have the kind of resolution in space like a camera has. So that is kind of the problem statement. So now with radar technology, with the benefits from range and velocity resolution, but the limitations of angle resolution, how can we solve some of these problems? And that's kind of one of the key challenges and opportunities for AI/ML in this space.
So you can't use beamforming? You
can, and that's how you get this angle. So first of all, this angle estimation is from beamforming, but it's got to do with how narrow the beam is. So that depends on the aperture of the antenna. So if you have a larger aperture, which means more antenna elements, then you can get a narrow beam, and that will give you a more angular resolution. But if you want a small form factor, let's say you're trying to put some 2 transmitters and 3 receivers in this 6 mm width, that is going to have an aperture which is small, and therefore the resolution is not going to be very good. So if you put a sensor, radar sensor with many elements, and you have a large aperture, then you can get a very high resolution with the radar as well.
But that's only for FMCW, right? What about if you use code domain radar, right?
It's true for any radar, I mean, irrespective of the modulation. So the angle resolution is directly a function of the antenna aperture.
But I've seen like in code domain, you can use dithering to get super resolution. Like
So-
you don't have to.
Yeah, so there are super resolution techniques that can solve some of these problems algorithmically, but the native angle resolution is directly a function of the aperture. Super resolution techniques do help, and that can help with getting, there are techniques like music and other algorithmic approaches. Sparse arrays is one way where you don't need to have all the elements, you can have a lot of zeros, and you try to improve angle resolution through algorithmic approaches. So there are techniques, but at the end of the day, if you compare radar versus vision, right, one of the key differences or disadvantages that you would say is that you don't get the picture of a person from a radar. You would get a few points for a typical low-cost radar. But then you also have the benefit of range and velocity. So how do you put all of this together and solve some of the problems like classification using radar?
But also you could do SAR imaging, right? But
you can do SAR imaging, but that again is like extending the aperture. Yeah, extending the aperture with movement of the single sensor. Yeah. So SAR is also a possibility. Yeah.
Yeah, so can we do any better with multiple radars in the picture, which not a single radar?
Yeah, so that's also another technique. People do distributed aperture where you can have 2 radars, for example, which operate in a coherent way. And that's kind of, again, a way of extending the aperture. At the end of the day, all of these are techniques that, whether it is SAR, which is physical movement, or whether it is multiple radars where you're trying to distribute the elements, it's all basically boiling down to wider aperture to improve the angle resolution. Yeah.
What is the percentage accuracy, whatever we are doing? What is the percentage of accuracy we get?
So that depends on the scene. Like for example, a strong target, you will have very high accuracy. You could, for example, in range, you can get millimeter level accuracy, for example. For angles, you can get down to less than a degree. It depends on what is the target and what is the configuration also. If you use more bandwidth, you get more range accuracy. If you use more antennas, you use more angle accuracy. You get more angle accuracy. Yeah.
Is it possible with your chips, you mentioned 6 antennas per chip, to do this synthetic aperture, matching coherence between chips, or do they just output range and velocity?
So that would be an extension of what the chip natively does. So in synthetic aperture, you are physically moving the chip, and you are
extending the aperture by having multiple chips.
So that would require synchronization, which is possible with some of our devices, but not all. Yeah. So here, so this is a little bit of a tutorial mode in the context of the workshop projects. Just giving you an overview of FMCW radar. So historically, there have been many types of radars used. pulse radar, CW radar, code modulated radar. But the most commonly used scheme in automotive radar today, and also in all of our devices, is FMCW, frequency modulated continuous wave radar. So here the waveform is comprised of a set of chirp signals, where you start at a certain RF frequency, let's say 76 gigahertz, and then you linearly increase the frequency or linearly decrease the frequency, let's say up to 77 gigahertz, for example. So you create the sawtooth waveform, like the red waveform, that's the transmit signal. And then this waveform is radiated and it hits the object, comes back, and the received signal is mixed with the same transmit signal. And so what you measure, the received signal is the black signal, what you measure is the beat frequency, and that has information about how far the object is. So that's the basic idea. And why this modulation scheme is very useful or has benefits is that you can sweep a wide RF bandwidth. You can sweep like 4 gigahertz of bandwidth, but you don't need a 4 gigahertz digitizing at the ADC level, because you're only measuring the beat frequency. So the beat frequency would be typically a few megahertz only. So the main benefit of this modulation scheme is that you get very good range resolution without having to do gigasamples per second ADC and gigasamples per second processing. You can just do less than 15 megahertz of IF processing and you're able to get all the information. So that's the big advantage of FMCW radar. It also has lower peak power requirement compared to, let's say, pulsed radar, where you're concentrating all the energy in pulses. Here you're continuously transmitting, so the energy is spread out, the peak power requirements go down. So radar sensors do measure what we call as the radial distance, the distance in radial direction, radial relative velocity. These both will be measured precisely, and it can give angle information using multiple transmitters and receivers. And we'll talk about exactly how the processing works in the next few slides. And the factors that determine the performance: the range precision is proportional to the RF bandwidth, the velocity precision is proportional to how much you're transmitting, how many milliseconds you're transmitting, and the angle precision will be dependent on the aperture or number of transmitters and receivers. So this is typically this is the heat map. So I'll explain this more as we talk more about the processing.
One question.
Yeah.
Like when in a traffic stop, when there are 10 or 15 cars around, like the FMCW radars from like adjacent cars are going to interfere with each other. So how are you going to ensure that? Are you applying some type of coding on top of it?
So one thing is that today that is becoming a bigger and bigger problem in the industry as more and more cars are getting deployed with radar. So interference is becoming a big problem, but it is not very bad, because at the end of the day, if you have two cars which are using, let's say, the same band, let's say 76 to 77 gigahertz, and two cars are using it, they are not always colliding, and that's because they are both sweeping the 76 to 77 gigahertz band, but only when they cross each other, only when their RF frequencies cross each other to within this 15 megahertz, only at those points you will have interference. At the rest of the points there is no interference, because it gets filtered out. So in that sense, there will be occasional glitches in the received data. So you have interference causing ADC data corruption. Maybe if you have a set of samples, maybe some samples got corrupted when that crossing happens. But that can be solved. You can do algorithmic techniques. You can look for glitches. You can detect those, and there are techniques you can do to mitigate it. And there is also sparsity available in the scene. Usually, radar signals, the received signal is sparse in the sense that you might have an object here, you might have an object there, and there is a lot of noise. So the sparse signal recovery mechanisms can be used to mitigate the interference. So you reconstruct what you lost. The few samples that you lost, you can reconstruct. So there are various techniques, from very simple techniques to very advanced techniques, going all the way to compressive sensing and so on. So there are techniques available to mitigate interference. But it's not as bad that just because there are two cars which are both using 76 to 77 gigahertz, both will completely die. That's not the case. Yeah.
I have a question.
Yeah.
So there are different ways in which you can use FMCW. One is an up chirp, one is a down chirp.
Yes.
And you can have a sequence of up chirp and a down chirp.
Yes.
Is there a particular reason why you always go with up chirp?
No, it's up chirps and down chirps are both equal and both can be used. The one that you're referring to, which is a bunch of up chirps and a bunch of down chirps, that is, we call that a stepped FMCW. So this is just regular FMCW. There is a variant of it called stepped FMCW. So that has a different set of properties when it comes to range resolution. So for example, here, the range resolution will be dependent on this bandwidth of each chirp. Whereas if you try to do a lot of up chirps, the effective range resolution you can get will be the overall bandwidth of all the chirps put together. So effectively you are getting a better range resolution, even though each chirp itself is only transmitting, let's say 200 megahertz. You stack up many of them and you sweep 1 gigahertz, so or 2 gigahertz, and that gives you a better range resolution. So it has a different, it's a way of improving range resolution, you can say.
Also, once you have generated an up chirp, in the hardware you also have to bring that frequency down to the next sort of a sequence to do it. Then why don't you go for an up chirp, down chirp sequence, which would be more hardware friendly, I suppose?
So it's got to do with the processing. So maybe when I go to the next slide, I'll explain that if you have a sequence of up chirps, that's the most simplistic thing you can do. The processing involves just doing some FFT within each chirp and across chirps. Whereas if you do up and down, then the Doppler that you get from the up chirps and the Doppler that you get from the down chirps will not have exactly the same behavior, right? So it's not, that's a more complex scheme. It's doable, but typically to keep processing kind of simple and elegant, people, the most commonly used technique is just this regular FMCW. But stepped FMCW is also a popular way.
But also, if you can modulate this chirp signature, right, that also would give a lot of interesting signatures, right, which probably not be explored. I mean,
You mean like non-linear?
Yeah.
Yeah, I mean, again, the processing is the question, right? A linear FMCW has this advantage that whatever received signal you're getting, the beat frequency is directly proportional to the distance. That's it. So you just do an FFT and you're done. But if you're doing something non-linear, then it becomes more complicated. How do you then extract the distance, right? So it is more complicated. But I mean, if we are talking about, let's say, AIML techniques, then anyway the network has to figure it out, and maybe non-linear techniques could become interesting if you're anyway feeding it to a network and letting the network figure it out. Then it doesn't have to be a linear FMCW. But for conventional signal processing, a linear FMCW gives a good starting point because you can get this range Doppler heat map by doing just 2 FFTs in range and Doppler, and you directly get the heat map, and then the network can take over from this point. Whereas if you do something non-linear, then you can't get to this heat map in the first place.
So there's no limitation from the RF front-end side, right? That you have to have this, because anyway it's some voltage control oscillators, right?
I mean, it could be built. It is possible to build something that can do non-linear modulation. It may not be that current devices can do it, but from a circuit design perspective, non-linear should be possible because depending on exactly the architecture, if it is voltage control oscillator, then you can do a non-linear sweep of the voltage. If it is a different technique like a digital loop, then you can still give codes which sweep the codes non-linearly and make it follow that non-linear waveform. So it is possible. It's got to do with what does it take to do the processing in that case. Yeah.
So can you comment on like what's the advantage of FMCW or code domain? Because that's another.
Yeah, code domain again will have the problem of if you try to do these codes, for example, to get a certain range resolution, you will end up again running these codes at chipping rates of gigasamples per second. If you want 1 gigahertz RF bandwidth, and because you want good range resolution, so you sweep 1 gigahertz RF bandwidth, you would run, let's say, a code which has a chipping rate of 1 gigachips per second. Now, to digitize that, you need ADCs which are very, very high sampling rate. So the compute becomes.
So it's mainly on the processing side.
It's mainly on the processing and also the circuit design side because and power consumption, cost. So those become the challenges.
But if you could do, because there are some of these work where people are doing correlators
Yes.
for these domain radar. Then is there a specific advantage of FMCW technique over?
It's again power consumption, cost, and compute. So those are the advantages. Yeah. Okay. So this is giving a little more detail about just a block diagram of how this radar would look like. So you have this ramp waveform that's generated. So the local oscillator is designed to generate the RF following this ramp waveform, and that is transmitted out, and the received signal is received, and you beat it with the transmit signal, and you get the IF, which is digitized and then processed using a DSP. So as I mentioned earlier, the transmit signal, if that is the red waveform, then you have the received signal from various objects in front, and those are the black and gray waveforms, and all you have to do is take the received signal and do an FFT. You get a beat frequency spectrum, and all the objects in front will appear as tones in the beat frequency spectrum, and that directly gives the distance to the different objects. So that's how the range measurement is done. Now, how do we measure velocity? Velocity is measured by looking at, when you do many such chirps, the phase change from the signal from this chirp and this chirp and this chirp, the phase change gives the velocity information. So that's how the relative velocity is measured. So that's very high level overview of how range and Doppler measurement works. And how does angle measurement work? Like you mentioned, angle measurement is directly from beamforming. So you have the signal coming from a certain direction, it goes through different path lengths as it comes to the different antennas. And these antennas could be the receive elements, but these could also be what we call virtual elements. So if you have 2 transmitters and 3 receivers, you can configure the array to give 6 virtual elements. So the 6 virtual elements receive the signal, and again, depending on how much the phase has changed between these elements, you can do a 3rd dimension FFT to measure that phase change, and that directly gives the angle information.
One question.
Yeah.
Since your antennas are on package, I believe there will be a good amount of mutual coupling between the antennas, and that will degrade this estimated angular resolution. So, this formula assumes, I believe, no coupling between the antennas.
Yeah. So, definitely coupling is a problem. It's not only for antenna on package; it's also a problem when you put them on the PCB, for example, right? Even then, there will be a coupling issue. So, it's about how much isolation we can design it for. So, we of course try to design it to have good isolation so that the angle estimation, the ideal angle estimation formulas will work. But again, it is also possible to do advanced calibration techniques. For example, you could, at production, when you make the sensor, depends on the application. At production, if you need better accuracy than what is natively available from the standard FFT approach, you could do a calibration where you can put some corner reflectors, we call it, or some known objects at different angles, collect all the signatures of the mutual coupling or the angle distortions, and then in the final deployment you can leverage that and correct for it. So those algorithmic techniques are possible.
Are they really uniformly distributed? Wouldn't beamforming be better used for non-uniform distribution?
This is kind of like a textbook tutorial, but basically this is a uniform linear array as an example, and this allows you to again just do an FFT because you're just looking for a phase change in this uniform array, and whatever is the 3rd dimension FFT, the peak, wherever you find the peak, that will directly give you this angle information, right, or this omega, this phase change information, which then maps to the angle. If you do something non-linear, then you have to do more advanced processing.
Non-uniform.
Sorry, non-uniform, yeah. If you do non-uniform linear array, so for example, let's say you have not the same spacing between elements, you could do something like you can put them still on a uniform grid with some missing elements. So that would be one thing. And there you could start by saying, okay, I'm just going to put zeros in the middle. So that would be one example, but that will have side lobes and other issues. So non-uniform spacing typically has side lobe problems. But it's not that it's not used, it's still used. It kind of goes back to sparse arrays, sparse array techniques, compressive sensing, and so on. Yeah.
Excuse me.
Yeah.
Does the dummy antenna improve the angle resolution? Dummy antenna. Like in some of your products, there are dummy antennas.
No, the dummy antennas are just to solve the, just to give more symmetry. I mean, when you have non-idealities like he asked about, right, isolation and other problems, right? So we have some dummy antennas on the sides just to make all antennas have similar surrounding. That improves the matching between the elements and reduces the challenges with the non-idealities. So it allows you to do simple processing basically. But that does not give you any signal. Yeah. So this is then the processing flow in typical radar signal processing. So I mentioned that we have some pre-processing of the ADC data, then you do a first dimension FFT to get the distance, then the Doppler, and then at the output of this you have what's called a 2D heat map, which is a range and Doppler heat map. So if you have a car in front, then it will show up as a peak in the range Doppler heat map, and then you can do detection, and for those objects you can also do angle estimation using the multiple received signals from the various antennas, and then you can do clustering and tracking. So this is a typical ADAS processing chain. Okay, but what we wanted to talk about here is not the typical chain, but where can ML help in millimeter wave radar. And I mentioned yesterday that echolocation is common in nature. You have bats and whales and dolphins using echolocation. So in that context, for addressing some of these variety of new applications that are emerging, there are newer challenges in these applications. For example, you just are not trying to detect objects, you're trying to see if you can do classification. And that's becoming important for many use cases. For example, classification can mean using radar for human-computer interface like gesture detection. Kick to open is another gesture type example for automotive. In-cabin child presence detection, occupant classification. So here, for example, you probably don't want radar to trigger an alert if the person in the car is an adult. You probably only want to do it if there is a child left behind. So can you detect a child versus an adult using the signatures from the radar? Elderly fall detection has some elderly person, when you're doing occupancy sensing, in case the elderly person has fallen down, can you detect that? And this again has applications in industrial and consumer electronics context. Surface classification, target classification, this is applicable even for ADAS, where vulnerable road user detection is an important application. So when you have radars in cars, you can detect objects, but maybe you want to classify whether there is a vulnerable road user. Vulnerable road user is like pedestrians, cyclists are vulnerable road users, and can we classify that so that the driving algorithms can use that information. So this is from a paper in the IEEE Signal Processing magazine, which again talks about a lot of the indoor monitoring use cases going all the way from security and people counting and intruder detection to telemedicine, vital sign monitoring, and so on. Assisted living, I mentioned fall detection and other applications. Sleep monitoring is an important application. Smart environments, lighting, energy efficiency, human-computer interaction, which is gestures. So these are all kind of these emerging applications, and in these applications, classification using radar is an important problem statement, and that's where a combination of regular signal processing and AIML techniques can come in. And what are the challenges with, let's say, a problem statement like occupancy sensing? First of all, we talked about the limited angular resolution. So the point cloud from a radar after detection is not going to look like a human, right? Unlike a camera. So there is going to be spreading in angle domain. It limits the point cloud accuracy. You have static clutter. So typically in any indoor environment, you're going to have furniture. You're going to have so much static clutter, which are not of interest. Maybe those are just inanimate objects. They are not of interest. but then those will also produce reflections. So definitely static clutter is a challenge. Now you can use the Doppler signature and only detect moving objects, but moving objects can also have different types. For example, there could be moving objects which are not human. Not everything that's moving is a human being. For example, you can have curtains or fans which are moving and have a Doppler signature, but you don't want to trigger on those. You want to trigger only on a human movement, right? So non-human moving objects is a problem because it causes false detections. And you can also have the opposite. You can have humans who are sitting very still or sleeping or something like that. So now the Doppler signature from that human being is difficult to distinguish from static clutter, right? Yet there is enough information in there because there is still some movement, there is breathing, vital signs and so on, which give some signature. So making sure that, separating out a static but still a human being and making sure that that person is detected. So that is another challenge. Multipath reflections, non-line of sight conditions. So you can have situations where the radar is reflecting from a smooth surface, and so that creates an illusion as if the person is somewhere else. So that is a problem. Non-line of sight conditions, the signal can be very weak. For example, in the child presence detect case I mentioned, inside a car, the child might have slid into the footwell of the car, and so it's not direct line of sight and it's difficult to detect due to weak signals. So these are all challenges, and how do we solve some of the classification problems like detecting static versus human versus non-human conditions. How do you select the AI features? Do you process the entire range angle heat map? Do you process after the points and just run some network on the point cloud? Do you use what's called microdoppler? So these are kind of the different challenges that one could look at. So in TI we have studied microdoppler signatures, given that these high frequency radars have good velocity resolution. So the velocity signature for the different objects are different. For example, a human being walking around can have a certain microdoppler signature with or without arm movement. Fans have a different signature. Curtain blowing can have a different signature. Dog can have a different signature, and so on. So there is information available to help classify. So and that makes the whole thing promising, and these signatures can be used to do the target classification. And so there can be different approaches that one could take. I just listed down a couple of approaches, but there can be many other approaches. One could be that the full heat map can be fed to a convolutional neural network and CNN, RNN type approach based on the full heat map. And that's one way you could do classification. For example, we have looked into that for the child presence detect case, where we've studied whether we can distinguish between a baby versus child versus an adult using the heat map itself trained on these three classes. Similarly, one could do something else. This is an approach where you extract some features. For example, rather than feed the entire heat map, you extract some average Doppler and range. So this kind of approach we have tried for gesture recognition, for example, where we condense the information into a few features, and then the compute for the neural network is much lesser, and using that, running through a simple small network with extracted features is also a possibility. So there is a wide variety of approaches possible depending on the problem statement. And I just have listed down a few case studies from literature which you can look into to get inspiration for what kind of approaches different people have taken. So for example, this is one where, this is from TI, where we have done gesture recognition using this feature extraction approach. So it runs on our device with an integrated DSP. And this is a very low compute requirement approach, and it gives very high accuracy. So this is one approach that we have taken. We also have done other, there are also other papers from TI related to child presence detect and so on. Then there are other papers and literature you can find. There is CNN-based gesture recognition approach where the entire range velocity heat map is fed into a network and you get the classification. So here they have achieved 88% accuracy for 11 gestures using this approach. Similarly, you can look at the microdoppler signature like I mentioned. So the microdoppler information can be again used to classify. So this paper talks about classifying whether the person is, what the activity is, what the human activity is. So whether he's walking or running or jumping, the activity classification is being done using a microdoppler signature, and they have again got good accuracy. Okay, and this is an example where they have used radar to do a vulnerable road user classification. So in the ADAS context, using radar to figure out is it a pedestrian or a cyclist or a car. So 3 categories, and again they've shown that they have got good accuracy with radar based classification. So these are just some examples for the different approaches that can be used to solve some of the problems. Now that said, one of the unique challenges for radar is, unlike in the vision domain, there is a paucity of publicly available data sets. So it's not like a camera where you get millions of images every day to train on. Vision domain is, the data set availability is very good. Whereas in radar, that is not easy because first of all, it's not easy to agree on a standard format. The signaling itself depends on what configuration for the chirps. I mentioned that you can use different RF frequencies, different bandwidths, different durations of the chirps. You could do stepped FMCW, regular FMCW. So there are different ways of designing the transmit waveform itself. So there is no standard in this. That's one. And also, they are all tailored depending on the performance and memory trade-offs. So for example, like I mentioned, long-range radars versus short-range radars, the chirp configurations are very different. And depending on the objectives, the waveforms itself are designed differently. So it's unlike a camera where, you pretty much, it's a standard thing, you take a photo, you get what you expect. Whereas here, there is so much additional detail to it that makes it difficult to arrive at a standard format. Similarly, in terms of the network also, there are so many possibilities. You might even start with raw point cloud as your starting point, or you might start with the raw ADC data, or you might start with the heat map. So unlike an image, the starting point is also variable. So these are kind of unique challenges in the radar space. So that's kind of the overview for AI/ML applications in radar. And with that, I will summarize. So millimeter wave radar sensors have a wide variety of applications, going well beyond automotive radars. There's people monitoring, motion fall detection, health monitoring. And these applications require classification, which is an emerging area of interest. The sensors have very good range and velocity resolution, but spatial resolution is limited. That's what makes the problem more challenging. But there is scope for AI/ML techniques, and these are being used. But it is still in the early days because of the challenges associated with it, and there is more work that needs to be done here. And this is an opportunity for further research and development to enable all these newer use cases. So that was my last slide.